Hey, what's up? It's your old pal, Mr. Cook, and we were finishing up this Unit 6 test review on logs and exponents. So the very last page of the review is all about graphing. So if you have a graphing calculator, it's, extremely easy to do these graphs. Like I'll give you an example. I'm going to show you how to do this by hand, but, just really quickly, some of the easier ones, like, okay. I'm going to show you how to graph the difficult ones, like number 40, number 44, number 43. I'm going to show you how to do those ones using your graphing calculator, just because I don't want to spend so much time working on those, by hand. But I'll show you how to do the graphs real quick. They're all pretty easy. So if I want to type in this number 40, I just do y is equal to 2 times parentheses 1 over 2 to the power of x plus 1, so x plus 1, and then minus 2. And then if I hit table, so go to second, and then graph, that'll bring us up this table. You can scroll up and down and find coordinates to graph out. That's really helpful, because you can just look for the ones that fit on here. So like, negative 4, 14 will fit on there, so negative 4, 14, there's a coordinate. Negative 3, 6, so negative 3 and then up 6. Negative 2, 2, so left 2, up 2. And then negative 1, 0, so left 1, up 0. 0, negative 1, 1, negative 1.5. And 2, let's see where 2 is. So you can just use the arrows to scroll down. The numbers keep getting closer and closer to negative 2 on the y-axis. So what happens is that this graph just keeps going down and down and down and down, and then it gets real close to 2, but never actually quite gets there. So like this is a really tough graph. Don't expect one that's this difficult on the test, but just know that you can type it into your calculator and get a really easy graph just by going to the table. I'll show you how to do the other ones as well using just your graphing calculator. So even a logarithm, it's pretty easy. You just hit y equals, and then, use the log base. I'll do this one with the log base for the calculators like this, and I'll do this one without log base. For some of your calculators might not have that function. So I hit math, press up a couple times, do log base, and then I can type it in exactly as written, 1/4, and then x plus 6, and then the outside of the parentheses minus 3. So I go to my, hit second and then table, and I can just graph out any points that I can. So obviously I can't graph any of these error ones, so I'm going to do like negative 5, negative 3, so left 5, down 3, and then I've got negative 4, negative 3.5, so negative 4, then down 3.5, and then negative 3, and then it's even closer to negative 4, so negative 3, negative 4, like right around there. And then I have negative 2, negative 4 on the dot. There we go. Let's see what other ones I have. 2, negative 4.5, so over 2, down 4.5. Any other ones that I want to graph out? Let's see. Yeah, there's one. 10, negative 5. Looks like 10, negative 5 is like a bit off the graph, but you can kind of get an idea of what's going on. The graph goes this way, and then it goes through these points here and here and here. And notice that like it cuts off and the x value is negative 6. We're going to see why that is in just a second when we do the domains and the ranges. So we're going to leave the graph like this for now, but just know that like logs have this little funky thing that goes on, which is real similar to the exponents, where they have like a horizontal asymptote here. They're going to have a vertical asymptote, and we'll see that it comes from like the x part of this in a second. I'll also graph out number 44, but I'm going to use the graphing calculator and not the log-based stuff. So if you don't have log-based, you can still type this into your calculator, and it looks something like this. So you do the log of this part, the parentheses, so hit log, and then x minus 1, and then divide that by the log of the base, so log of 1 over 3. And I'm just using the regular log button right here, and then minus 2 at the end, so minus 2. So what I did with all that stuff with the dividing and all that, that was just this part of it. So then I had to do minus 2 at the very end afterwards. And I'm going to get, the graph for this. I'm just going to go to the table again, And you notice that I have a ton of errors already, but then I have a couple coordinates that I can graph out, like 2, -2, so over 2, down 2, so right there. And then I got another one at 4, -3, so over 4, down 3. Let's see if there's any other ones up here. 10, -4, so that's off the graph, down 4. But it looks like the graph's going to pass through those points and then kind of stop at 2. So we'll see why that's the case in a little bit as well. All right, so let's leave our log graphs like that until we get to the domains and the ranges, and then, you know, graph all these by hand. All right, so if you have a graphing calculator, this is a piece of cake. If you don't have a graphing calculator, that's all right. You don't have to worry about it. You can still graph all of this stuff out. It just takes a little bit more time. So instead of, you know, graphing it out and taking some time with that, let's do the stuff that's easy on this first, like the domain and the range of all of these things. So with exponents, the domain for any exponent expression depends on what x values that you plug in, right? Well, for exponents, with a very, very few exceptions, you know, especially in our class, we're not going to have any exceptions to this rule. Your domain, your x values, you can plug in any x value that you want. So that means that the domain for any of the exponents that you're going to see on the test is going to be all real numbers. So you can just write in your all real numbers symbol, or you can write in all real numbers if you want. It's going to be the same for any exponent, like any exponential expression that you see. The log functions, that's going to be the same for their ranges because they're inverse functions from one another. And we'll see that in a second. So now for the ranges. All right, the range is entirely dependent on what's adding or subtracting outside of the function, outside of the exponent. So your range is always built around your y values. So whatever is adding or subtracting outside of the exponent, in this case it's 1, we're going to put that next to the y. And in this case it's -2, we're going to put that next to the y. As long as your exponent is positive overall, your y value is going to be bigger. So if there was like a negative in the front of this 2, like that, then this y value would be smaller than 1. The reason that that's the case is because the exponent values are going to keep getting more and more positive. So the y values are going to keep getting more and more positive, and they're going to be bigger than that value 1. Because the smallest number that this could ever be is 0. And so that means that the smallest value that y could ever be is 0 plus 1, so 1. That's why y is always bigger than 1. Same thing goes here. If that was like a -2 on there, then that means that the y would be smaller than -2, but since it's not negative, y is going to be bigger than -2. So see how easy the range of the domain is? The domain is all real numbers whenever you have an exponent. The range is just whatever is adding or subtracting outside the exponent. Y is going to be bigger than that if it's positive, smaller than that if it's negative. Now look at the range and the domain for these ones. These are so easy, it's ridiculous for logs. You'd think that they'd be really difficult because logs are kind of weird looking and they have all these bizarre properties that go along with them, right? But actually the log, domain, and range is really, really easy. So for all of these logs, every single one of the log expressions, in our class, every one of them is going to be all real numbers for the range. Every single one of them. So that's like really easy to catch on to. The exponents have domains that are all real numbers. The logs have ranges that are all real numbers. Now the domains are even really easy for logs. All you have to do is just select the values that are inside the parentheses here, underline them, and set that value equal to 0. And then solve for x. So to get x by itself, we subtract 4, so we get x is equal to -4. So we write, for the domains, we write x and -4. You know, and then for this one, x minus 1 equals 0. So add 1 to both sides, x equals 1. So we write x and 1. And we're going to fill in the inequality in a second, okay? So just write down the numbers for all these. X plus 6 equals 0, so x is equal to -6. So we write x and -6. And then the last one, x minus 1 equals 0. So solve it, x is equal to 1. So x and 1. All right, now here's how you get the domains for these. For any logarithm function, for any logarithmic function, this whole thing needs to be positive. It has to be positive, okay? So as long as your x value is positive, whatever you got when you solve for 0, x has to be bigger than that number. So x is bigger than -4. That's the domain for this one. X is bigger than 1 for number 42. X has to be bigger than -6 for number 43, and x has to be bigger than 1 for number 44. Now, if we go back over to these graphs that we had almost completed, this tells us the rest of the story, because if the domain is -6, that means that the x values, there's basically like a wall that shows up at -6 on the x-axis, and our graph can't go past that. So we can get really close to it, but never actually pass it. So the remainder of the log function goes like this. Same thing over here. Our x values on this graph can't go past 1. So that means that if we draw a vertical line at 1, our line can't go past there, so that means that it just goes up along the line but never passes it. It's kind of like a barrier for that graph. So this is the completed log function. That's all that you need to do for those ones. Let's start drawing in some of those things over here, like for number 41, we're going to have that wall that shows up at -4, so at -4 we're just going to draw a vertical line in there. And then at 1 we're going to draw in a vertical line over there, because that's what the domains do. They make these little vertical lines, the barriers that the graph can't go past. Believe it or not, we actually have those same things with the exponent expressions, because the range tells us that these are like the floors or the ceiling for these graphs. So -2 is this like line right here. It's a horizontal line that graph can't go past. And we even showed that with the little coordinates that we got there. For this graph, our ceiling, or our floor in this case, is going to be at 1. So we just draw a horizontal line through 1. So it's safe to say that when you have an exponent, there's going to be a floor on the graph, and you can find that from the range. And for logs, there's going to be a barrier, like a wall, that the graph can't go past, and that's going to be part of the domain. So you can graph those things on there really, really easily from that. Okay, now to graph like 1 or 2 of these just by hand, and then we'll do the transformations. So the graph of this exponent by hand, all you have to do is make a t-chart and plug in values for x. I'd highly recommend just plugging in, say -2 and -1 and 0 and 1 and 2. If you're thinking next level graphing, you should really center it around whatever value you have here. So like I'd center it around -2, so I'd go up and down 2 from -2. But this will just kind of have to do for our graph. So if we plug in -2 to here, you can just use your calculator for the rest of this, plug in and get your coordinates. So if we have our equation and then we have our x values to plug in, we have, let's quit out of this. So 2 times 2 to the power of, and then I'm going to plug in -2 for x, so -2 plus 2, and then plus 1, and I get 3. So -2, 3 is one of my coordinates, and I'm going to plug in -1. So -1, 2 times 2 to the power of -1 plus 2, and then plus 1, and I get 5. So there's another coordinate, -1, 5, and I'm going to plug in 0, 2 times 2 to the power of 0 plus 2, and then plus 1, and I get 9 for that one. Now I'm going to plug in 1, 2 times 2 to the power of 1 plus 2 plus 1, and I get 17. Let's see, 17 on the graph? Yeah, and it looks like if the numbers keep getting bigger, so at 2, it's going to be too big. Let's verify that, though, just by plugging it in. 2 times 2 to the power of 2 plus 2, and then plus 1. Yeah, 33, that's way too big, so that's not going to fit on the graph. So what we're going to do is graph the coordinates that we have. -2, 3, so go to the left 2, up 3, so 1, 2, 3, there's 1 point. -1, 5, so to the left 1, up 5. 0, 9, so up 9. 1, 17, so over 1, up 17. And so our graph, because it's exponential, is going to go through those points, so through here, through here, through here, through here, and then it's going to go along the little floor that we've created and just follow directly down that path. So that's the graph of our exponential expression. So we have 2 exponents graphed out, and we see that even graphing it by hand is not that bad. As long as you have a calculator, it's pretty easy. Okay, let's see how the log fares. Well, with the log, what the best option that I've seen to do with the logarithm is to just kind of take the log expression and convert it to something easy, an exponent. So I'm going to use that rule that we had back at the beginning of the lesson, where it's a to the x equals y is the same thing as log base a of y equals x. So I'm going to turn this from a log into an exponent. So the way that I do that is just by, first getting the y value attached to this -1, so I'd add 1 to both sides. So that gives me y plus 1 equals log base 3. Let me erase some of this so I have a little bit more room to write. Oops. Log base 3 of x plus 4. So now that I have it as a logarithm, like this, I'm going to rewrite it as an exponent. So my base is a, so it's 3, so 3 to the power of, and then my power is right here, so it equals that y plus 1, so y plus 1 goes up there, equals whatever in the parentheses, so in this case it's x plus 4. Then get the x value by itself, so subtract 4 from both sides, and you get 3 to the power of y plus 1 minus 4 equals x. Now this looks an awful lot like the graphs that we just did, doesn't it? So what we can do is, again, just make a t-chart and plug in -2, -1, 0, 1, and 2. But here is where it gets a little bit weird. We're going to plug those numbers in for the y value instead. So along the y values here, we're going to plug in -1, -2, and then 0, 1, and 2. So let's plug those numbers in using our calculator. So that's the only thing that's a little bit strange about doing this by hand. It's obviously a lot easier if you have a graphing calculator, so that's probably the recommended choice, borrowing one of your pals' graphing calculators, or an older brother, older sister that doesn't use it any longer. If you can get your hands on a graphing calculator, I recommend using it. So I'm going to plug in -2, -2, plus 1, and then minus 4. And what number do I get there? So -3.6 repeating, okay? Let's plug in -1. So I get 3 to the power of -1 plus 1, and then minus 4, and I get -3. Okay, now let's plug in the 0. So I get 3 to the power of 0 plus 1 minus 4, and I get -1. So these aren't that bad to graph out. And then I've got 1 that I'm going to plug in for y, so 3 to the power of 1 plus 1, and then minus 4. Oops, minus 4, there we go. And I get 5. And then the last one I'm going to plug in is 2, so 3 to the power of 2 plus 1, and then minus 4, and I get 23. So that's way too big for my graph, but at least I got a couple other coordinates to graph. So let's graph those ones out. 5, 1, so go over 5, and then up 1, there's one coordinate. -1, 0, so go to the left 1, and then up 0. -3, -1, so go to the left 3, and then down 1. And then -3.6, so pretty close to -4, -2. So -4, -2, somewhere right there. And this tells me that my graph's going to go like this, pass through these points, and then run into that wall and just go straight down along the wall. So there's my log graph. And I'll just do this one a little bit faster, number 42, but it's going to be the same exact steps. So I'd turn it into an exponent first. So I've got, let's see here, I got to add the 3 over to both sides. So y plus 3 is equal to log base 6 of x minus 1. Then turn it into an exponent, so 6 to the power of y plus 3 is equal to x minus 1. Then add 1 to both sides, so 6 to the power of y plus 3 plus 1 equals x. Now I make my t-chart. I'm going to plug in the same numbers for y, -2, -1, 0, 1, and 2, and then graph it out. Okay, so let's see here. Let's plug those numbers into here. 6 to the power of -2 plus 3, and then plus 1, I get 7. All right, now try -1. So I've got 6 to the power of -1 plus 3 plus 1. I got 37. Oh boy, so that's already huge. So that means that the more numbers that I plug in this way, it's probably going to get even more, crazy big. So I'm not going to plug in watch, if I plug in 0, it's going to get humongous still. So watch, 6 to the power of 0 plus 3 plus 1, 217. Yeah, yikes. So these points aren't even going to be on there. So it looks like the more positive that I get, the more gigantic the numbers get. So what I'm going to do is go more negative instead and see if that helps out. So the problem like this probably wouldn't be on the test. So, don't worry too much about a graph like this. Usually they're a lot easier to do, and especially with like a base like 6, we wouldn't do something like that, I don't think. So I'm going to plug in instead -3, -4, -5, and -6, and see if those numbers get me a little bit closer to something that I can actually graph out. Okay, so I'm going to plug in -3 in for my y value. I get 6 to the power of, and then it's going to be -3 plus 3, and then plus 1. Oh, that's a lot easier. 2, there we go. Now let's try -4, so I plug in 6 to the power of -4 plus 3 plus 1, and I get 1.16 repeating, 1.16 repeating. Let's try -5, 6 to the power of -5 plus 3 plus 1, 1.027 repeating, and then -6. So let's try that one out. 6 to the power of -6 plus 3 plus 1. And I get a little bit more than 1.004. Okay, so let's graph these ones out. Maybe that'll make a little bit more sense of our graph. We've got 7, -2, so I go over to 7 and then down 2. 1, 2, there we go. 2, -3, so go over to 2 and then down 3. There we go. Barely over 1, -4, so over 1, -4. And then a little bit past over 1, down 4, 5, 6. So it looks like our graph is going to go through this point, and then straight down here like that. That's just how a log looks. Okay, so that's our graphs all done. Now there's one last thing that we need to do, and that's the transformations. And I know this video is already getting a little bit long, but the transformations are pretty easy as well. Here's how the transformations look on our graph. I should probably do it at the top of the page. Here we go. All of your exponent graphs are going to look like this. Y equals, and then you might have a number times your exponent, so b to the power of x, and your x value you might add or subtract some number onto it. And then aside from multiplying on your exponent, you could add a number on your exponent, and that can change it up a little bit too. So here's how the transformations happen with this. With a, if a is negative, then that means that you have a reflection of your graph, and it's over the x-axis. If your a value, regardless of the sign of it, if it's positive or negative, if that a value is bigger than 1, then that means that you have something called a vertical stretch. I'm just going to write VS next to it for vertical stretch. If my a value is less than 1, I have something different. It's called a vertical compression. It kind of like squishes the graph down vertically, so that's VC. I'll call it VC for vertical compression. If I have a C value, if I have the number that's adding or subtracting onto the x, if the C value is positive, then that means that my whole graph gets moved over to the left by C, however much C is. If C is negative, then that means the whole graph is moved over to the right by that amount C. And then my D value, if the D value is positive, it moves the whole graph up by D. And if the D value is negative, it moves the whole graph down by D. And these same transformations are going to be true for exponents and also for logs. So if I write it up like that, y is equal to a times log base b, whatever the b value is, of x plus c plus d. So it's the same type of transformations and all that stuff for exponents and also for logs. So let's just remember where all that placement is. A is a number that's multiplying out front. C is a number that's adding or subtracting on x. D is a number that's adding or subtracting outside of the function itself. So looking at number 39, I have a number that's multiplying out front, and it's 2. So that means that since that number is bigger than 1, I have a vertical stretch. So one of my transformations is a vertical stretch. Another thing that I have is a number that's adding or subtracting onto the x. So that's C. So that means that it's either going to move to the left or to the right. Since it's adding, it's going to move to the left. So it moves to the left by 2 units because it's adding 2. So left by 2. Then the graph is adding 1. So if I'm adding some number, that's D, and that moves the graph either up or down. And since it's adding, it moves the graph up. So it's going to move it up by 1. The transformations are another part of the graphs that are really easy, so long as you just remember, if it's on the x, it's moving left or right. If it's not adding onto the x, it's moving up or down. And then if it's multiplying in front, it's either going to be a vertical stretch or vertical compression, or it's going to have a reflection over the x-axis. Doesn't look like we have any negatives on any of these, so we're not going to have any reflections. So, don't worry about that one, I guess, for this page. But just keep in mind, these parts, and it'll be pretty easy. I have another 2 out front. That's the a value, so that means that I've got a number that is greater than 1, so it's a vertical stretch. I also have another that's adding on to the x value, so that means that since it's adding 1, that means it moves to the left by 1. And then I have a -2 outside of that, so that means it's going to be moving down by 2. So those are the 3 transformations that graph has. All right, now on to the logs. It's the same kind of rule. Do I have a number multiplying up front? No, so I don't have a vertical stretch or vertical compression. But I do have a number adding on to x. It's +4. So that moves it to the left or to the right. Here's an easy way to remember. If a number is adding on to the x, just remember the direction that x can go. The x-axis goes left and right. So that means it's either going to move to the left or to the right. Since it's adding, it's moving to the left, so left by 4. That's the transformation that goes on there. And then since you have a -1 outside the parentheses, that's going to move the graph up or down. And since it's negative, it moves the graph down by 1. Now for the transformations for number 42. All right, so transformations for that one. All right, so we have a -1 inside the graph, so it's going to move the graph to the right by 1. And then we have a -3 outside of the parentheses, so that's going to move the whole graph down by 3. And those are the only transformations there. For number 43, we're adding 6, so our transformation is that it's going to be moving to the left by 6, so left 6. And then we have a -3 outside, so that's going to move the whole graph down by 3. And then the last one that we have are the transformations for this one. Now, since we're subtracting 1 on the x, that's going to move the whole graph to the right by 1. And then so we have -2 outside the parentheses, that's going to move the whole graph down by 2. And those are the 2 transformations that are possible there. All right, that's almost a 30-minute video. My goodness, I should have probably broke that up into different parts. But if you got all the way through this one, then that's a nice little tutorial on the graphing that you're going to see. There's only going to be 1 exponent and 1 log graph, so don't think that we're going to have this many graphs on the test. Don't think that we're that mean. We wouldn't do that to you. But if you do need some extra help on this stuff, don't be afraid to reach out to your teacher. I hope this was helpful, and good luck on your test.